little bit simpler, but the next trick to do is to do a variable substitution. And that variable substitution is the following. New variable eta will be xa minus key. X will be xb. Which is xb minus ke xa. And then the estimate of that, xb hat minus key is equal to xb estimate minus ke xa. Xa is not an estimate, that's measured. Right? So there's two new variables. In terms of the So we can simplify some things here by playing a hat to be a, b, b, minus k, b, a, b. Basically this part. Okay, I can do a matrix. There's a new b matrix. So I'll say that's combining all of the parts here. That's a hat k, e. Plus A, B, A, minus K, E, J, K, A. Our matrix F here is B, B, minus K, E, B, A. So this whole thing simplifies greatly to something that's actually trackable here. So it's in this kind of a state form that we've always been using. It just happens to be these matrices you've got to figure out. And eta, remember, is x, b hat minus k, b, y. That's the definition. And u is still theta dash hat. If you look at that, this is Ka, Kb. Ka is from our known state. Kb is from our unknown ones. Y and Kb. Because y is our known state. We're able to measure that. this is simply minus KAY minus KB. Vector of those, which are multiple of those. So these are measured. These are estimated. So our U, I can rewrite as the following. Where KA and KB are the controller gains, KD is the estimator gain. So if we put that into this, right? I know what U is now. We can almost get this thing down to a usable form. Almost. Here's our equation. A minus F hat KB times eta hat. So that's kind of our new observer, minimum observer A matrix. And then everything else here. So this will define as a tilde. B tilde will define as this whole part. And our C is minus KB. And our D matrix, so we have a D matrix now, is minus KA plus KB. So I have new A, B, and C D matrices. Okay. So our state observer system looks like the following. It's a mess, but doable. All right, here's an example which I left in my office. Apologize for that. Which we can do that Thursday. And then also want to start in on the inputs to the system. So it's a little bit trickier to implement these minimum forward observers, but these advantage is that it should have fewer delays and fewer, the minimal number of estimated I need, the better. Yeah.
Should that be in hat?
Yeah, should be. They're all in the hats. They're all in the hats. Everything's in the hat. I apologize for that. Two sets of notes and I left them on my desk. So, questions, anything? Labs, homeworks, anything? Finish up? Yeah.
So we started out with like AAA,
Yeah.
like AB.
Yes.
Where did we get
Well,
those?
X, from the state equations, and I'm splitting this up into things I know I'm measuring and things I don't know. I
Okay.
have to estimate. So you split up all these parts. So the A matrix, I'll split up into the parts that go with XA, or AAA, right? The parts of XA that multiply times XB, called A, B, and then vice versa here.
Okay, so we
By
just,
simply partitioning A matrix.
okay, so we just divide up our original A matrix.
I'm not dividing, it's partitioning. Yeah. So for instance, example here, let's say, my simple side order here. 0, 1, minus 1, minus 2. AAA is 0, AAB is 1, ABA is minus 1, ABB is 2. I'm simply partitioning out different parts. Then using those for all these massive equations. Yeah.
If you have 3 states, would it then be like you can divide, you just maybe have, if you have one state here you can actually measure,
Well,
and then you have 2 that are the
I'll have
XB?
2 that I estimate. An example of that. So let's say, so these are the ones I have to estimate. Now usually I always put the one I can measure on top, all right, just for convenience. Makes the partition simpler. So let's. Here's the numbers. In this case, X1 is XA. XB is X2, X3. Okay, that will be a vector. Vectors, all these are vectors, even scalars are vectors. So my AA, in this case, is 0. My AAB is 1, 0, 2, 3. My ABA is 1, 2, minus 1, minus 4. And, oh, sorry.
1, 0.
This is 1, 0. No, this is 1, 0. This one is 1 minus 1. Then A, B, B is 2, 3, minus 4, minus 5. So they're all square, that doesn't matter in this approach. And of course, my BA is 2, BB is 1, 3, and C is always 1, 0, 0. I'll put 1 there because that's the one I'm measuring. partition.
One more question, if you had two that you were measuring, would your C matrix be 1, 1, 0?
Yes, it would be. So if I have two of them that I can directly measure, so this would be XA in that case would be X1, X2, XB, which would be X3, and partitions for. Right. So my A would then be 0, 1, 1, 2, be 0, minus 1, and this would be minus 5. Yeah. That says I only have to estimate for one variable. The other two I can directly measure. Okay. Any questions in this? I said, I'll give you an example. Thursday, yeah.
Does this have to be used for?
No, doesn't have to be. Good question. When would you want to use a minimum order observer? When would you not want to? Or not care?
Like, if the sensor is expensive or something, could you potentially?
Well, it's going to, hardware. So if I want to use a really good sensor that I don't need to filter, is it worth it? Good question. Or these are more difficult to implement. They're much more complex than a forward observer. Forward observer, really pretty straightforward to put together. These are a little bit messier to do. As you'll see an example, where you'll do a nice second order work. See, they're a little more tricky to put together. As opposed to, well, even if I could measure, let's say, X1 directly, why not just go ahead and estimate it anyway? Is there that much harm? Maybe not. It may not matter that much. Because a full order observer is much easier to implement than a minimum order. But I only use a minimum order one to really have to operate the over time. We'll get into another thing at the end of the class, which is, how do you get this gains for these things? Basically by pole placement. I'm defining where my poles, my estimator ought to be, and I'll figure out the gains to make those poles happen. There's another way of doing it, is I look at the noise of the system, of the signals, and base the gain to minimize that noise. That's what's called a counter filter. Different approach, but it's one that directly says, what I need to do is filter this feedback noise. Right? And it might filter less. And we'll do that one. Introduce the concepts of it. It gets pretty hairy to go through the whole thing. It involves what's called radiation patterns. We do that in optical controls. Take optical controls. All right. Other questions? All right. Have to run short today. But the notes when I was. Hey, it's after all breaks. Thanks everybody who came to first. Why don't you there? Hope you slept in.